I was doing some of those exercises
Yeah.
practice. What do you do if it's a metalloid? Is that just
Metal
considered
alloy-
a non-metal then still?
It's treated as a non-metal.
As a non-metal? Okay. That's what I thought.
Well, most of the problem. Alright. Okay, so let's continue on Chapter-3. We're probably not finished Chapter-3, and we will just study like a few seconds, and then we will do the lab. Alright, so far now we are doing the calculation of the so-called molecular mass. Alright, molecular mass referring to the mass of one molecular or one formula unit. Depending on what we have. Usually when we have those compounds, we call them a molecular compound, and we call them a molecule. But for some type of compound, like those ionic compound, there is no moleculars, the so-called moleculars, and we only have the formula unit. Okay, for example, the common example is NaCl. You don't call NaCl is a molecule of NaCl. So this just the name. But when you do the calculation, if you have the formula, you just read the formula carefully, see what is in the formula, and you calculate like what is the total mass. For this example, what we did Tuesday, I think most of you get it right. So this compound is also ionic. For the ionic compound or the molecular compound, obviously you want to get the formula first to calculate the formula mass. Alright, so this ionic compound has the formula, the Ca3 and PO4 like that. Right. So once you have the formula, you can call the formula you get some of those special names. Okay. For the molecular compound, what you get, we call that a molecular formula because it exists as like a species, we call that a molecular. And for the ionic compound, you can call that a formula unit. But once you have those formula, you do the calculations, and I think that is an important concept I want to emphasize, which means not for two of those units, or not for two of those molecules, or for 10 or whatever the numbers, just for one. For one of those formula units or molecular, the mass is very small, so therefore the convenient unit is AMU. And you can see in this CRE, all those answers is AMU. So because it's referring to one of these formula units. Convenient. And you can use some other units. You can use a gram, but you use gram, your number will be different than those numbers. You have to convert the AMU into grams. Right? But if you don't want to do any conversions, you just calculate what is the mass or what is the weight of one molecular. You just use the molecular formula and use the periodic table and calculate. Right? Any questions? Right. So next concept is the molar mass. Molar mass. So this is referring to mass of 1 mole something. 1 mole something. And then we know 1 mole of something or 1 more anything actually is a special name or equals equivalent to the Avogadro number 6.022 times 10 to the positive 23, that much of something. So therefore, in this calculation, we understand what we really get is the mass or the weight of that much of something. Not only 1, not 2. Okay? It's that much of something. The calculation, well, the concept is different, but the calculation is the same. You just identify the formula for the compound. The formula may be molecular formula, maybe formula unit. As we said, if your compound is a molecular compound, then your formula is a molecular formula. And if a compound is an ionic compound and you don't have a molecular, and you will have those formula units. So you still like compare, you still do the calculation similarly. If you want to calculate again for like 1 of this molecular water, and you identify the water molecular formula is H2O, so therefore it has 2 H for each 1 water molecular and 1 O for each 1 water molecular. You want to get the total mass of 1 H2O molecular, just identify this information, then use the periodic table, and you find out the mass for 1 H atom is 1.01 AMU, and the mass for 1 oxygen atom is 16.00 AMU. So you multiply it, you get 18.02 AMU. So this is the curve for 1 molecular, 1 water molecular. So let's like stay on the same pace, okay? So we study like everything like together. Right, so then you can calculate like 1 mole of H2O or 1 mole of NaCl, which means you want to get the mass of Avogadro number, that much of H2O together, and conservatively totally different than the mass of 1 H2O molecular. But because the definition of 1 mole something is that number, and also because we know that much of AMU, 1 AMU is 1 AMU. If you have Avogadro number of AMU, and that becomes like 1 gram. Right? So you don't have to do the conversion. Don't worry about the conversions. So what do? You just read the formula carefully, see how much what atom in it. H2 again, you have 2H, 1O. You want to calculate the mass of Avogadro number of that much of water. You just take that number from the periodic table again. You know the H is 1.01 and the oxygen is 16.00. So what do? You will take 2 times 1.01, then very similar as what you did for the calculation for 1 water molecular. You do exactly the same, but your unit will be different. Because this time you not calculate again for 1 H2O molecular is for Avogadro number, that amount of H2O molecular. Alright, so I think we emphasize enough, which means you can calculate the mass of 1 molecular or 1 formula unit, that will be AMU per molecular, or you can calculate what is the mass for 1 Avogadro number, that kind of connection of some of those molecular formula units, and you will get numerically exactly the same number, but the unit change into grams. Okay. And also emphasize, or just I want you to review what we learned before. So this concept is very, very fundamental, very basic concept in chemistry, which means you have to know this 1 mole, this word actually is a special name for like that amount of number. Like 1,000 in our daily life we know is 12, and then one more in chemistry is this number. Right, so I add this slide and to summarize, because otherwise I will write on the board. And to summarize what we learned in Chapter 2, and then we are going to use what we learned in this chapter to repeating these few important conversions. And so I give them like even some special name called GMN or AMG. So G is standing for gram, and M is standing for mole, N is standing for numbers. So you can convert between any of those two letters. You can go in from G to M, and then you can go from M to N, or you can go reverse from N to M, and from M to G. So those are not new. So just different way to memorize them, and different way to use it. Right. So if you want to convert from gram to moles, and then you use the so-called molar mass. Molar mass, I'm right here. So this is our step 1. Use molar mass. Molar mass depend on the problem, depend on the compound. So what we learn in Chapter 2 is molar mass for some of those elements, which is very simple. You can find the molar mass, for example, for carbon. Chapter 2. Molar mass for C is 12.01 gram equals 1 mole. So that's what we learned in Chapter 2. You can read this number very quick from the periodic table. Then you can use this equation and to change this equation or use this equation as a fraction. If you are given gram, like what we said here in this direction, if you want to go from gram to moles, you have to somehow make the right fraction. And here you are going to, for this example, you're going to use 1 mole on top and 12.01 gram at the bottom. So this is one example of use molar mass to convert from gram to moles. Right. So the second step, you can convert the moles into numbers. Use the Avogadro's number. Avogadro's number, as we write before, is in this definition, or in this name. 1 mole equals 6.022 times 10 to the positive 23. And then this number is universal. No matter what problem you have, no matter what compound you have, or what atom you have, if you think about 1 mole, you always think about this number. Right. So now if I have this mole after I convert from the gram, use that first fraction into the mole, that means we already have how much mole. Then you want to continue convert how much mole into numbers, just use this fraction. Right. So if you can see, that means I'm going to put that Avogadro number on the top and the mole at the bottom. Right. So then you can do the reverse. Okay, now let's do the reverse. That means I'm going to go from the numbers into the moles. And for both of these steps, in between more and numbers, no matter you go from more to numbers or from number to more, you just use the similar fractions. You can use the Avogadro number, but it might have different. Like the fraction might look different. So for this example, if you want to go from number to mores, you are going to do something like this. So you get more on the top, and then 6.022 times 10 to the 23 at the bottom. That means, let me put them in the parentheses, because otherwise the line can kind of confusing. Right. So these two fractions you use either from the more to numbers, or from number to mores. And you can see both of these two fractions has this number, the so-called Avogadro number. But this Avogadro number appears in the fraction at a totally different place. When you go from more to numbers, it's on the top. When you do the reverse from number to mores, it's at the bottom. And you don't have to mechanically spend a lot of time to memorize, like going what way to multiply by what. You just try, and when you set out those problems, depending on what it gives you, then you see if you can cancel out what it gives you. Okay? If you set out the fraction, if you forget, instead of multiply by that number, divide by that number, you set out the numbers with the unit, and if you say, if you cannot cancel out the given unit, then you quickly do a quicker change, just simply flip. Right, then similarly for this, so if I want to go from the mole to grams, I will do the 12.01 gram and over 1 mole. Again, let me put this in the parentheses, because yours, the parentheses is too long. Right, so these two steps is very important, and in these first few chapters of Chemistry 101, you are going to see a lot of those similar steps. And then right now we should like study very good, spending a lot of time doing more exercise, making sure you can understand these few steps. And there's a lot of similar steps as this to pretty much just give you some units, you find out the equation between the two units, and then you just write those as fractions. Alright, so this is what I said, the two common steps. Obviously I have like here, I have 4 steps, but two steps means you're going from one direction, 2 steps, and you can go reverse 2 steps. But common like those, and some problem probably you don't have all the 2 steps or 4 steps. You might only need 1 step, depending on the problem. Right, so make sure we study those these few steps. Right, any questions? Right, so let's see this problem, okay? And so this example, I will do this example, and you will do some of those similar CREs. So we have an aspirin tablet, okay? And it has 325 milligram of citrus salicylic acid. That's a special common name for one of those organic compounds which has some of those medical effects, and give you the formula like this. Once you have the formula, we learn in today's first slide, we can calculate the molecular mass or the molar mass. And I can use it to do some of the conversions. So then the question is, give you this much gram or milligram, and did not give you the gram directly, but you can convert into grams. Then you are repeating what we did this 2 steps from gram to mole, from mole to numbers. And I ask you this much milligram of this compound has how many molecular, which means how many of these together, C9H8O4 together as molecular unit. Alright, so this will be the typical program. You can see this, you will be our, you probably have to do a little bit more work. This will be the from gram to moles to numbers, so the GMM problems. And G is gram, now you have milligrams, so therefore you have adding one more step. So then our conceptual plan, so our strategy will be from the mg, and we'll go to g, then from the g we will go to the more, then from the more we will go to the number. And when you write those conceptual plan out, or you think about in your brain, in your mind, you should think about each step need what equation. Right? So the first step, you want to converting from milligram to gram, you want to use this 1000 mg equals 1g, this equation. And then the next two steps, so we already talked about that in the last slide, from gram, let me just make some arbitrary line, from gram to moles, you use molar mass, and then from mole to numbers, you use that Avogadro's number. All right. So let's get started on the first step, and even though the second step we need to take a break to calculate what is the molar mass. Right. So if I give you 325 mg right after that, okay, and you see the first, we are going to use converting fraction, so therefore the first converting fraction will come from the first equation, and the first equation has 1000 mg equals 1g, and what you do, you just decide, as I said before, you can quickly come out like some kind of like a hypothesis. You see, let me try, I put that milligram at the bottom, the gram on the top, we can do the reverse, before you'll see that is wrong, but you just try one try, see if you can cancel out the given unit. Okay? So if I do the reverse, if I do like 1 gram at the bottom, and then I try 1000 milligram on the top, and so each time you use the conversion fraction, before you going forward, just check if you can cancel out the unit you don't want. Usually the unit you don't want is the unit given to you because you want to use what given to you to find something else. So you can see here, you cannot cancel out the g with g, even though that looks like that two letters the same, but totally standing for different things, right? So therefore, just do a very quick like a reverse, right? So I'm going to just reverse those problems because we already say that doesn't work. So therefore, you can just put 1000 mg here and 1g on top, and then you can see your calculations. So if you want to see what we did in chapter 2 or chapter 1, so this mg is exactly the same. Okay? You can even add more information that with what we're studying in chapter 4. Mg of what? More of what? Okay? So you have to cancel out exactly everything the same. Okay, any questions? Any questions? Alright, so let me use this pen and continue to the second fraction, or the second step. If you can read, what do we use in the second step? So this is our step 1, this is our step 2, this is our step 3. What do we use in step 2?
We have to divide by the total number of carbons, hydrogens, and oxygens in that.
What do we call that? What is the name of that? Molar mass, okay? So let's use this property here, let's calculate. So we need the molar mass of C9, H8, and O4, right? And what we learned in this chapter, you want to calculate the molar mass, you take see the numbers, how many carbon we have, how many H we have, how many oxygen we have. So this formula tells us we have 9 carbon, right? And then you just find the number for carbon from the periodic table. What is the number for carbon? 12.01. So we have 12.01. And you want to calculate the molar mass, then those units will be gram per mole. So we can add those units all together at the end. Right? And then we will see the next element. The next element is H. And we have 8H. And then each one H, So here on the table you can see there are different numbers, but usually I will prefer, I will do the problem, I will running those numbers you get from the periodic table with 2 decimal places. So you can see here 12.01 has 2 decimal places, and then for each I will do the same, I will use 1.01. And so then next one we have oxygen, we have 4 oxygen, and you read the table, is 16.00, so each number you get from the periodic table will have 2 decimal places, so that will usually that will be enough for the precision, because you want to get a little more precise than what you get from the experiment. Right? So if you do the calculation, anyone need the calculation yet? Mike, did you get the calculation? What is the molar mass of this aspirin?
Yeah, I didn't divide it.
So let's see, we have 12.01 times 9 plus 180.15. Right? Same? 180, right? 180.15. What is the unit? What will be the unit? The unit? What do we calculate? Yeah. So it will be gram per mole. Gram per mole. Okay? So what we learn in chapter 2, when you have this information, you can write something like this. You can write 180.15 gram over 1 mole. Okay? Or you can reverse flip this fraction. Okay? So when you have this already looks like a fraction. So you have gram on the top, mole at the bottom. What you did is just adding a number. And instead of just mole, you see the per mole means 1 mole. Right? And for every equation, like those equations what we did for on this slide, we have this 1000 mg equal 1g. For every equation or relation or equivalent, whatever we call that. So whenever we have those kind of information, a unit, another unit, you can always write 2 fractions. So the other fraction will be 1 mole over 180.15 gram. And now let me put this in the parentheses because that will be very easier to see. So we have 2 fractions. Okay? And once you have those in your mind, and you should be able to get that very easy. So right now we cancel out the mg, we get the g, and you want to go forward again, you want to get away from the g, you want to cancel out the g. Right? So these 2 fractions, and both of them have the g. Okay? So if you choose the first fraction, your g will be also on the top. Then both g on the top, on the same side of the equation, which means right now we are multiplied, you cannot cancel out. Right, so therefore, as what Mike said, you will take this 180.15 g and 1 mole. So that means you divide by 9 carbon plus 8 H plus 4 O, those numbers, which means the molar mass. Right? So let's see the calculations. So you can see the calculation will be very good. So this gram and this gram. So the gram comes out. So each step, make sure you do those checks. So if you use the right fraction, so you know count out the g, you get more, right? And then if you can see again the last step, you want to get you want to go from the mole to numbers. What do we use to go from number from mole to numbers? Avogadro number. Avogadro number, which means you will see that equation. You can write that out or not. That means you will have that 1 mole of anything equals 6.022 times 10 to the 23 anything. If you do those quite often, then you will see that all those are equivalent. You can write as an equation, or you can write as 2 fractions. So if you have that, and let me erase this information here, and so I can write this information into 1 mole over 6.02 and 2 times to the power of 23. So this is 1 fraction, or this same information, and 1 mole here, and you can see these 2 fractions, and just exactly the reverse. Any questions? What's the question?
I don't see why you put the 61022 on the top, not, or on the.
We did not decide which one to use yet.
Oh, okay.
So we just said, I said, whenever you see an equation, then in the front, whenever you see the equation, so whatever you see the equation, that means you have two fractions. Right, so you can see this. Then let's go back to the problem. So right now, what unit we have and where is that unit?
Milligrams?
More, where is more? On top or at the bottom? On top. Okay, so on top, if in the equation you can have like one on the top, the other on the top, on two sides, you can cancel out. But if you're not in the equation, which means you are just putting all, string all those conversion fractions together, they have to add the opposite place. So we are at the opposite place. Right, so which fraction shall we use? The first one or this one? This one, right? Yeah. So we are going to use this 1 more here and 6.022 times 10 to the 23. That looks like, right? So then you have this, feeling. So you see, like you should get the right number, and you should get the right fraction, right? Right. So I think that's the reason. Now let me change that into back into this color, so then you can see this more cancel out. Right. So then what you do now, just do the calculation. Just everything here is multiply or divide, and you review like those significant figures. So make sure you do that right. Right. So 325 divided by 1,000. 1,000. So this number here, as what we learned in chapter 1, is exact number. Exact number. So that is from definition. Okay. Exact number here. Exact number here. Okay. And exact number here. And exact number here. Okay. Right. So then once you do that, so we do that, and so we will divide by 180.15, and then we'll times 6.022, and what you get, 1.0864 times 10 to the 21. So I keep all those digits, but you can review very quickly. So how much digits shall we keep? Where shall we run in our answer? 3 as f, right? Okay, so we have 1.09 times 10 to the 21. 21 what? 21 this. C9, H8, and O4 as a whole. Okay, so let me say this is a whole. That's complete. And that's everything together as one something. And pretty soon you're going to learn for every one something, for every one aspirin, for every one water, you have to be able to identify how many H do you have, how many O do you have. Once you have that information, you can do more steps. Okay? So right now we calculate, we have this much atom together as a molecule. We have that much, we have about 10 to the 21. And you can calculate, if you have 10 to the 21, 1.09 times 10 to the 21, this together, then you can figure out very quick how many H atoms do you have, or how many oxygen atoms do you have. So you can use the proportions for every one of these. How many H? 8 H. Okay? For every one of them have 8 H, and you have that much, this together, you want to find out how many H, and just multiply by 8, but we'll talk about that more in details. Alright, so far we just stop at this step, so therefore we find out in this much compound, even though initially we have the milligram, so after we do a few calculations, we find out it has that much of that C9H8O4 together as aspirin. So you take aspirin for the headache. So you take my tablet, you take that amount of molecules. Right, so I think you have the diagnose, so you should be able to know that two very important steps, GMA and MG. You don't, sometimes you don't have to use all those steps. So here we have a few of those problems, and you want to get, you want to compare who has more, okay? So therefore you probably don't have to calculate those numbers, just somehow figure out how much more in each of those numbers. Right, so what we see, this more is very important. So more kind of in the middle. So you can convert and use the values like that. Right?
Is it E?
The answer is what?
E?
Oh, very good. Yeah, I like that. So you're doing liver like those readings before the class, and then usually to study. Okay? So study at the side is progressive, so you just learn little by little. Okay? Very good. So I think that you can see like the answer is easy. The first question is give you gram, and you want to go from gram to mole. So for the first one, what do you do? You want by the molar mass number. Okay, molar mass of CO2 is 44.01 gram and 1 mole. We inside this guy is called what? Molar mass. Right? So even though these two numbers is the same, so 44.1 gram, that is gives you how many gram of CO2. Okay? I put that in on purpose, the same number, because you get exactly 1 mole. Right? Now this number you get is not what I give to you, is what you get by using this formula and use the periodic table. Right? So you take that number given to you, divide by the number you get, and which is exactly 1, so therefore it's 1 mole. Right? Now this obviously tells you is 1 mole of that something. Okay? And again, you can get this mole, if I don't tell you, you can get that how much mole you have from either gram, or from numbers, or from some other information. If you have the gas, you can have the volume, you can have the temperatures. If you have solutions, you have the concentrations, volume. Right? And then numbers, the C is also very straightforward. Right? I think by now, in your mind, you will see this number is very kind of like just popping out of, jumping into your mind right away. Right? So whenever you see this number, that tell you very similar as that word darling, but it's not so small, because that is still like that concept that is that much of numbers, right? And then this number D is very similar. D is kilograms, right? Kilograms. So how you get how much more do you have? How you convert? So for this number, for this D, you have a gram, and you want to get more. What do you use again? Molar mass. So you just multiply by the molar mass. Now in this example, molar mass of what? Molar mass of 82. So 82 obviously just adding like 2H with 1 O, you get 18.02 gram and then 1 mole. So very similar. So I tell you again, this the first 18.02 is what I give to you, or the problem gives to you. And this number you get is from your calculation, from what you studied in the first few sessions. Right? Any questions? Right. So if I were you, this problem is give you the grams. And then you want to compare which one has more molecules. Obviously, you will have different molecules. Some not even non-molecular, so the other one is atoms. Just compare which one has more of those particles. So if I were you, I would probably just do the from gram, right? And from gram, you want to get numbers from gram to what? From gram to moles, then from mole to what? Into numbers. So probably I will do that. Okay? So after you do that, probably you will say, well, probably I don't have to do that. Okay? I mean, you probably you have this set out in your mind, but you probably don't have to do all those calculations. Right? So to find out which one has more. Huh? What do you get? A. Okay. Did you really do the calculation for each step, for each problem? Why not? Why not you do the calculation?
Because CH4 has the least amount of weight, so it would have the most amount
Dividing by the small number.
Okay, everyone hear that? Okay. So you can set up those calculations. You can set up that very common two-step. I tell you. So for each problems, let's see where so for let's see for the second one. So I have 10.0 gram C2H6. So what are the two steps? The two steps. The first step is from gram to mole. Right? From gram to mole, what do we use again? What do we use? What information we use? You want to convert it from gram to mole? Yeah, either from gram to mole or mole to gram use molar mass. And now let's see what is the molar mass of this guy. Roughly about 30, right? Everybody agree? So let's say 30 grams. Where I get the 30 grams? How do we know this 30 grams? Here with the formula. How many carbon we have? 2 carbon. Each carbon has how much? 12. So 12 times 2 is 24. Right? So how many H we have? 6 H. Each H has how much number? Probably about 1. So you have 24 plus 6 is 30. That's what we put here. Right? And then on the top you will have what? What will be on the top of this fraction? One more, that's more mass. Right? So what we saw here, those are very similar. So we put one more here. So this is my first fraction. So I cut out, and let me write those all similar. So I will write this kind out, and this kind out. Actually, now you get more. Okay, now what do we use in the second step? What do we use in the second step? Avogadro number, right? The Avogadro number again. Whenever you see the Avogadro number, you can think about this 3 different ways. You can write that as an equation or 2 different fractions. Okay? So those are always in your mind, but which one you use depends on the problem. Right? So for right now, we have the more, so I will just keep this one more here, then 6.022 times 10 to the 23. So I think that most of you get the idea. Okay? So I just did for one of these 4 problems. So I will do this. I will get this very similar setup for all the other 3. All the numbers are the same. 10 gram, 10 gram is the same, and this Avogadro number is the same. What the difference is this number here, because this number depends on the problem, right? So I think you are very, very right. So this, you calculate the molar mass. This mass will have the least molar mass, which is about 16, right? Understand? Okay. So you take a 10 and multiply by this similar here, but instead of this, for that first problem, what you have here is what? 16, right? And then this number is the same. Right. Any questions? Okay, let me write one more, because it seems you see, let me read this and write for the first one. Okay? So then you don't have to write everything. So for the first one, you have 10.0 gram of C4 times and 16 gram of C4, then 1 more of CH4, and then we will see this 1 more of CH4 is this number of CH4. Understand? You can see from this to the number, I think that will be enough. For this C and D is similar. So you can see, compare what we write out for A and B, everything are the same. You know, obviously those names are not the same. I mean, all the numbers are the same. You can save this number here. Right? So you have 16 for CH4. I have 30 for C2H6. And then when you compare, just compare which of those for calculation as this number smaller or larger. And you are going to use this number to the divide. So where we have a smallest number here, we have the largest overall result. That makes sense? Right? All right. Questions? So the answer is A, right? So medicine has 16, all the others is has more large numbers. All right. So now we are going to learn another type of conversion fractions, or those the so-called equations. The so-called mass, the percent compositions, and percent composition. You can have a percent composition of volume. You can have a percent composition of volume with mass. The commonly used is a percent composition of mass to mass. Right? So when we see this percent composition, you will see there's more, if you read the book, there's more some other percent. You can have those mass per like 100 volume. But commonly you use mass percent. When you have the mass percent, you can understand, you can have like some gram over the gram, or you can have the kilogram over the kilogram. So this so-called like those percent compositions. I starting with right very simple, gram over gram, kilogram over kilogram, but there is even more important information. Gram of what and gram of what, kilogram of what, kilogram of what. And you have to be able to clearly identify gram of what and kilogram of what. So in general, you are just adding those gram here into this part, or the kilogram here into those parts. You can use any same unit as long as the same unit. Right? So once you have this mass percent, which tell us how much gram of the part and in the so-called whole. And so that's sort of the compositions, because you have you can have what we saw before, like that what we call the whole. Let's say example, the whole is C9, H8, and O4. You don't have to figure out value, you don't memorize that. That's called aspirin, right? So you have that as a whole, and so you can have how much gram or how much kilogram of this as a whole, and I can also calculate or measure, for example, this part. Again, in one example, you can have other examples. How much carbon? The carbon will be the part. Or you can use other part. You can think about how many H. Well, how many, what units? So that's what I write on the top. As long as you have the same unit, then your result will be the same. You can use how much gram of carbons over how much gram of this as a whole, and that will be one example of the sort of mass percent. When I give you the mass percent, I probably will not give you the unit, or you cannot don't have a unit. Just like 34% of sodium, or like and so on. Right? So just understand this percent composition means one particular element or one particular type of element in the molecules compared with the molecule together. Right. I think this. Let's do a calculation, then we will follow like the step very carefully, then we'll see what we get, and you'll see that make sense what we talk about. We will calculate the mass percent of CL. So this is CL right here with our chlorine, not carbon I. It's like carbon and iodine. The CL together. So then you want to calculate the mass percent of this. You can either use the AMU when you do the calculations, or you can use the model mass. Just identify so our formula will be the part and over whole times 100, the percent compositions. Now what is our part here? Our part will emphasize on this CL. And what is our whole? So this is our part. Not exactly. We have to see part will refer to that. We have to see how many CL in there. Okay? So part is about the CL. Okay? Now what is our whole? So that is our whole. Right. So then let's see. We identify, let's see, first calculate this all together as a whole. Which means you can use what we did before. You can use AMU or use grams. So you can, but just use the same when you like to do the calculation. If on the top you use AMU, at the bottom you use AMU, right? So now we can see we have 2 carbons. So therefore I will take 2 times 12.1. And how many other we have? Well, for CL, CL is 35.45. And how many fluorine do we have? Right, so that is the whole. That means you just read like this formula carefully, see how many carbon we have, 2 carbon. How many CL do we have? We have 4 CL. And this number we get from the table, 12.01, you already know that before you don't have even use the table for carbon, just 12.01. And then this 19 is also from the table. Right? Understand? Okay. So 2, again, this number 2 from the formula. Okay. And this 4 from the formula. Okay. This 2 from the formula. Okay. 12.01, 35.45, 19.00, all from the table. Right. Then you calculate everything like in this formula. That means this is as one something is called whole. Right? Then you want to calculate those parts. So in this molecular, we have 2 carbon atom, and we have 4 Cl atom, and we have 2 fluorine atom. Now you want to calculate the mass percent of Cl. So therefore on the top we have 4 times 35.45, because our name is percent. Percent, so you per 100 part. Alright, so you do the calculation, and you don't forget to multiply by the 100, so 4 times 35.45, and divide by that, plus 2 times 12.01 plus 2 times 19, right? So you get 69.5711 and so on percent. And you can decide what unit we have. Well, this is the kind of problem. You can just see like, I think everyone has like 2 decimal places, and that's because we have 2 decimal places, and I think we will have like 4 SF, right? So we running now to 69.57% to get that, right? So what you get, now you have this percent, that means you don't have a unit. So what do you do? So later on, if you want to use this number to do some calculations, so that you understand, this can be written in like many different ways, okay? In many different units. for example, you can rewrite this as, so I have a 69.57 gram of Cl over 100 gram of C4, C2, and Cl4 and F2. So once you have this mass percent of Cl, in that Fourier, that one special type of Fourier, called the C2H Cl4 and F2, you can write up as this information. And as we said before, whenever you have a fraction, you can flip. You can write 100 gram of C2Cl4 and F2 over 69.57 gram of Cl. So these two fractions are actually very similar, just one is the flip of the other one. Alright. Now because in this number I did not tell you what are actually the unit. You can use a gram, you can use a kilogram, you can use a pound, you can use AMU. Okay? For example, I can use I just rewrite one of that. I can think about the 69.57 kilogram of Cl and over 100 kilogram of C2 Cl4 and F2 like that. And you can see this fraction, I put that in the parentheses, and so that fraction on the top and this fraction at the bottom, very similar, very similar. You can say this gram here is a kilogram there. Right? So once you have those mass percent, which means you can have many of those fractions, depending on what unit you have. Right? I think here important is compare these two. Right? And so that's about the mass percent. Any questions? Right. So this is your idea again. Probably you can think about just straightforward, use what I did for the example, calculate everything. Calculate the mass percent of H for everything. And then what you can use, use your results, figure out which one has the largest mass percent. A? Yeah, A is the answer. So all that has the same total mass. You can do the total mass doesn't matter for the mass percent. You want to get the mass percent, like for the example, what you do is just repeating what I did. For example, for A, what you want to calculate, just identify. So what our formula is part over whole times 100. Then I say, what is our part? Well, our part is referring to the age. Right? So how many age do we have? How many age do we have? In A, how many age do we have? 4. Yeah, so that will be our part. So you also remember, you don't simply use that element age or carbon, so you have to identify how many age in that formula. You have 4 age, and so then what will be the number for age? Just go to the periodic table, so that's 1.01. Right? Right. So now, what is our whole? Our whole will be the CH4, not only the H. So we have 1C, we also have 1C. Right? So 1 times 12.1, so that's because 1C. Okay? So this comes from 1C, plus 4 times 1.01, then times 100, right? So you do a calculation, and again, let me just, you can do the calculation exactly, but you can also use reasoning to figure out which one has more percentage of age. Right. So I will do the calculation later, and let me just write out another one for B. Okay. For B, we'll have a similar starting definition, so we have the part over the whole times 100. Now, what is our part in B? Our part is still referring to what? H. But how many H in B? 6 H. So we have 6 times 1.01. Now we will have a different formulas, therefore we have a different whole. So we have 2 times 12.01, then plus 6 times 1.01, and then times 100. Okay? You pretty much will set up the calculation for all those. This is one hint. So when you have those comparison problem, you compare which one has more, which one has less. The good idea is, for the purpose of save time, the good idea is either you write up those equations for all those problems, or think about those equations in your mind, and find out what is the difference. And then even, so once you do that, you don't even have to do calculation, you know like which one is more, which one is less. Alright? So that's what I want to say. So I think the answer is right. Right? So if you want to do a practice, so that's probably what we will study, was the way we study. So I will give you those starting point. Okay? So I'll give you the direction. If you want to do more practice, I think you should do more practice, and then just finish your level notes and do all those right up. Right, now we are going to use those mass percent as conversion fractions, conversion factors. Right, conversion factors, as I said in this first few chapter, I think until chapter 4 is very, very important. And later on in other chapters you still use it, but especially in the first 4 chapters, probably this is the most frequently used skill of solving problems. Right. So read the pattern, you will see the U.S. Food, Drug and Administration, the FDA, recommend that a person consume less than 2.4 grams of sodium per day. You will see like those food container has those information, and specifically it's about sodium, not the sodium chloride, not sodium carbonate, the sodium, this element by itself. Okay? So that's the reason we study the so-called mass percent. You have to identify mass, gram, kilogram of what element. So recommend you want to consuming less than 2.4 grams of Na by itself, not NaCl again. Okay? So what mass of sodium chloride, which is NaCl, in gram, can you consume and you still within that guiding line? And then in this problem, so it's kind of nice and give you the mass percent of sodium in the sodium chloride. But you don't have to. I mean, the problem don't have to give you those information. It will give you the compound name, and it should be enough. Because you can use what we studied in the last few programs. If you know the compound name, you can get the formula. Once you get the formula, you can get the mass percent of each element in it. Right? So this program again is nice. It's not only give you the name of the compound, and also give you the mass percent of sodium. Right? So what you do, you can rewrite this mass percent as what I did here into fractions, and you can write that as fractions. Okay? So let me circle this number here. Okay? So only if inside this number, you can see you have 39%. Percent means something over 100. Okay? So right now both don't have number, but you can write 39 over 100. Okay? So now 39 what? You have to be able to add on. Okay? You choose first what the unit. Because you are going to calculate those guys in grams. The problem asks you to calculate how much NaCl you can consume in gram. So therefore you decide for this given mass percent, you are going to use gram. And if you use gram for the number on the top, you also use gram for the number at the bottom. Okay, so let's add in little by little. So now we have the unit. And then we have to be more precise, say gram of what on the top and gram of what at the bottom. Okay, either you write out clearly or in your mind you should be very clear. For every step you're referring to what. Okay? You're referring to what unit and referring to what compound or what element. Okay? Right, so on the top is a gram of what? Very good. So Na, and you just write that very clear. Not NaCl, just Na. Okay? Now what is at the bottom? Gram, 100 gram of what?
Sodium chloride.
Sodium chloride, NaCl. Yeah. Right. So that's good. So that's very good. So then you have this fraction, and this fraction comes from this given information, 39%. So let me put this in the parentheses. Or let's keep the same unit. Okay. And from this fraction, let's write out another fraction. How can we get another fraction from this fraction?
The 100 grams of NaCl on the top.
Yeah, we got to flip that, right? We have 100 gram of NaCl on top, and I have 39 gram of Na at the bottom. Right? Right? So these first 4 chapters is about converting fractions, and that's the usual step. Okay, so when you have those information, try to think about there are 2 possible converting fractions. Now which one you use depends on what information, what other information is given to you. Okay? So the other information given to you is 2.4 gram of what? Very good. 2.4 gram of Na. So that's the information given to you. Right? And so therefore, you can start from that information given to you and convert that information into the gram of NaCl. Right? This is very easy to say. You want to calculate the mass of sodium chloride, which is NaCl. Right? So now what fraction should we use?
100 on top.
The 100 on the top. Right? Very good. So that's why we not see that makes sense or not. You didn't realize that yet. 39 gram of Na and 100 gram of NaCl. Well, I think that's right. Right? So once you have that either in your mind, you do a very quick check or just write that out, and you can see that gram of Na come out. All right. So what you do is just take 204 divided by 39, then times 100. Okay, so what do we get? 204 divided by 39 times 100. 6 point. So I run into the right number and NaCl. So that's it, right? We have 2 SF, and we have the unit in gram. And we know what are we referring to. We're referring to NaCl, not Na. All right. Any questions? problem, what mass of given name, you probably want to find out the formula, even though the question don't require you to find out the formula. Do a very similar calculation as what I did for the example. You can see even I give you the same information. Again, this information, you don't have to give that information. It kind of duplicates. So if I give you the name in the RN3 outside, and you should be able to find out the name I circled. All right. Let's see, everyone on the same line. Let me see your like procedure. Let me see your write up. Okay. What will give it to you? What will give it to you? Let me see. You write out what will give it to you. 58.7 gram of what? Let's start from that first. Or you can start from the mass percent. Gotta get to conversion corrections. So I'm going to take a break and see like what you do. Right? It seems you being a little slow.
Is it B?
Onto the B. Right. Okay. I think that makes sense, right? What it gives to you is the mass of the part, and then you want to find the mass of the whole. Then usually, the mass of the whole probably has more mass than the part, and that's like the check. See if you get the answer makes sense or not, right? So what it gives to you? Okay, Mike, you come here right up, like see what you get.
Oh, all right. I mean, if you just use process of elimination, you could probably get the right answer.
Yeah.
But,
So then you
correct.
right up, like see what a fraction use, like what you get a fraction from the mass percent. Right, then you see your right up. So what do you get? You get two fractions, right? So then decide what a fraction should we use. If you have the other information, the 58.7 gram of FE. 58.7 gram of FE. Pardon? That's, you have to recognize that. You get that right? You just use that. You just use like 58 is that divide by the max percent numbers. So you can.
Did you get it up?
No, that's right. All right, I see someone like what they did before. I think that's okay. So you can still use those proportions. So here is the proportion. What he uses is proportions.
I meant to.
He uses the proportions. What he write here? So this, right, Mike?
Yeah, I just did
So
it.
that means this will be what?
Damn it, Mike.
So this like that, right?
So
That's like
pretty
equals.
close.
He uses proportions.
Where did you get that paper?
We use the proportions.
What?
We use the proportions. Not a multiply. He uses a dot. I think that dot means.
What's that?
Alright, so everyone, I think you get the whole thing. 8.7 gram of FE. So this is my information given to you. Everyone agree? Right? And the other mass percent, So you know that 69.94
That's a badass.
gram, that mass percent number is referring to the part. Part of what? Part of FE.
I've seen all of
100 gram of FE203. You verify the formula is right, right? But I tell you the iron 3 oxide, and so you have the name, you want to get the formula.
I just watched it.
Just follow that 4 step or 5 step. You first get what is the symbol for iron 3, which is Fe3, right?
Dragon Ball.
So this has a symbol Fe3 part. This oxide has a symbol O2 negative. So how you switch, you get this formula right. Again, this what we study in this section is about the mass percent. Okay? So just remember that mass percent is the part in the whole. Any question or comment? You can use the property and what Mike writing here, or you can use what I did here is the conversion fraction.
Yeah, sorry for the confusion, guys.
Yeah.
No, it's already.
I
Right.
finally used
So
a
that-
calculator, I got the answer.
So as I emphasized many times, when you use the conversion fractions, just check it and see if you cancel out those guys. Okay? Again, in the calculation, you do not cancel something like this, like what we said in the first. You cannot cancel out this something like that. Okay? You cancel out exactly the same unit. Just not only like one measure cut out. So that's not right. Alright, so very similar. Again, this, okay, I don't have to give to you, I don't have to give you the mass percent of sodium chloride, because if I tell you the sodium chloride, and you should be able to find out what the mass percent of sodium, right? No. So be careful. Just so you starting with this information, and again I will say like you write out. I will ask someone to write out. Okay? Let's say you starting from what I pointed to. That is mass percent of sodium by mass. Okay. I want you to write that mass percent into 2 different fractions. So starting from that, you write 39 gram of Na over 100 gram of NaCl, then free weight, and then let me see which one you use.
Is it C?
The answer is C, right? What did you get? Oh, you just like see that yeah. You can do that if you know like you get it right. And if you want to make sure you get it right, you probably want to keep those units and see how you
I just.
see how you cancel out those units.
Yeah, I guess you're right. That's exactly yeah.
So what do you get? What do you get? Well, let me see how right now.
The way I did it, I just.
You get your fraction?
Yeah, that's exactly what I did. Plus all of them are like way freaking old. 850.
You want to write out and see what it is? Okay. Did you get that right? What is it?
I'm driving.
Always doing something like that. It's right at the beginning. If you have that, right now I have the tiny little dragon NaCl, and this NaCl at the bottom, 100 gram, and I see that the gram comes out. You know that, right? I'm hoping NaCl. Again. That's very good. You get that right?
Well, you're gonna be
Very
here,
good.
so
Yeah, this is
probably
NaCl, that's NaCl, so this comes out. You get it right out?
Wait, did you say physics in high school?
Very good, very good. So make sure you just, you do like what you need, from what you need. Very good.
It's
We're on
from
adding
St.
22 gram of NaCl. Because otherwise you don't, even though the gram comes out, but you don't know gram of what? So very good. 22 gram of NaCl. Right, the practice, very good. That's what you do. Very good. Okay. So you find about those, yes, so you got a second from like, very good, so that's, any questions? Do you like how you use PowerPoint? Yeah. Okay, any questions?
I mean, you just,
Yeah, you probably want to add in like a few of those units. Because write everything, especially at the beginning, there's a few problems. So write out 22 gram of what? Right? 22 gram of NaCl. All right, where you did? You did it here? Okay. Tell us what you, go over the procedure, see what you did.
I wrote 22 grams of NaCl times 39 grams of Na over 100 grams of NaCl. So I just multiplied 22 grams of Na by 39 grams.
Did the unit come out? What unit come out?
I just like used the numbers.
Okay, so you see the unit should come out too, right?
Yeah.
And this unit come out with what? The one on the bottom, right? Yeah. So you did that, but you can also show that, right? And then you can see what that over is a gram of, yeah, that's what you said, right? Okay, any questions? I think that's, if you learn something new at the beginning, just, learn like very clearly. Right, so now let's study those so-called converting factors in chemical formulas. I already mentioned briefly in that aspirin problem. Remember in that aspirin problem, what we calculate is 325 milligram, right? Use a couple of steps, you find out in that much milligram of C9H8O4, that's aspirin, right? And you find out 1.09 times 10 to the 21 C9H8O4. So you find out in that amount of gram of aspirin, and you find out you have that much as, again, you can call this, you can say this, if I put this in the parentheses as a whole, right? As a whole. Now this like a second is very similar to what you did like the mass percent, okay? Because you have this as a whole, and then you have all those parts. You can calculate the parts in gram, or you can calculate for every one of these units. Like one car has 4 door, 5 door, right? And you have this one molecular, that is 1. Then you can see how many carbon you have and how many H you have. Understand? And this is what we talk about in this section is those chemical formula you can use as conversion fractions. Okay? So for this one, I can write for each one C9H8O4. You can write equal obviously not straightforward. You can use something like that for the equivalent. So this means equivalent, right? Not really equal. You can say that not equal, just the equivalent. So for every one of these, and let's see how many C do we have? For every one of these as a molecular, how many C do we have? None. You can write out like many of those equations, depending on how many atoms you need. Right? So So therefore, if you know you have that much, these together, what we calculated in that example, and now you can use this equation and find out how many carbon atoms do you have. Right? So for example, I will write 1.09 here times 10 to the 21 C9H8O4, right? And that is I just thought about that problem, right? Talk about that problem when we have that problem, okay? So that means you can use those formula as conversion fractions. So we did some calculation to find out that much of aspirin. Or I will write here that slide looks like very, very confusing. 1.09 times 10 to the 21 C9H8O4. Okay? So we get this information from that problem, from that example, right? And now you can find out how much carbon atom we have. So we call this is our how many molecules. So we figure out this molecular as like one something as a whole, right? And so then we also like right here. So for every one C9H8O4 equivalent as 9C atom. 9C atom. You can talk about 1 mole or 1 mole. Obviously, what we get is that amount of molecule is not more. So therefore, you can use the same unit. Okay? And you can see here we talk about 1 mole to 2 mole ratios. You can use mole, or you can use atom with molecules, depending on what you use. Right? Depending on what we have. Now, what we have there is how many molecules. So therefore, you can see the molecular is comparable with how many atoms. Right? So now you want to use this information, and as I said, whenever you have an equation, or equivalence, sometimes you don't have those exact equations, like 2 equal to 2, that is that equation, and then those is called equivalent. You can make those conversion fractions. So now what do we do? We have this equation. Remember, whenever we have an equation, you can think about it, you have 2 fractions, right? So what fraction shall we use? Which one?
Carbon atom over 1.
Yeah. So you have 9C atom on top. Right? Then you have 1 of this C9H8 and O4. So this molecular, so this side here, that is there, because you can see you already have this, so this will come out. And this sort of those formula units as conversion fractions. So you have 1. Well, you can always think about for 1 is simple, right? And you can think about 2. Then you have, if you tell 2, then you have like 18 of those. And per 1, that's much easier. Understand? So those formula units always give you something like this. So you have this. Start with 1 is easy. 1 equivalent to 9. Then you can see like 2 equivalent to 18. But you obviously don't want to use that. Alright. So that is how we use those formulae as conversion ratios. So that is one example. Right. So I have this compound is ionic. You don't call this in the molecular, you call it a formula unit. But at least will tell you for each one of the formula unit and how much carbon you have, how much arsenic you have. And so now we do the similar programs. So I will write up for every one of these CaCO3 equivalent to like 1 Ca atom, if I call this is 1 unit. And you can also write, if you make that, if you make the unit larger, so then we write another relation, I can write one more CO3 and equivalent to one more of Ca atoms. Right? So just, you still have this similar 1-to-1 ratio, and you can use the same units. If on the left side, use 1 more, and then on the right side, have 1 more. If on the left side, when you refer to that as a whole, is 1 of those units, and then you will see how many explicitly how many atoms we have, not 1 more, not 1 dozen. That makes sense? And obviously you can have all those atoms here, you can have like let's keep using more because it's about more here, because we use this one more. You can write 1 more of CO3 equivalent to 1 more of carbon, and we will say plus 1 more of CO3 and equivalent to more of O. And now you tell me what will be the number for the last one. 3, right? So this will be the 3. Right? Now let's see, we have the information is 1.7 more of CO3, and what you want to find out is what? So that is the other information gives you, and not only the formula, the other information gives you is 1.7 more of this added together, and we have all those 1 more of something, or that something, and equivalent to different atoms. In this case, which one shall we use? What are we asking for?
Here you go. Awesome.
Then we will do what? Which one? Use the first one, or use the second one, or use this one? The last one, because we want to figure out how much more of O we have, right? So again, what shall we put on the top? You see the 3 O? Yeah, so that's right. So that's right here. 3 more of O on the top, and 1 more of CO3 at the bottom. Understand? Right, so now you can see those calculations. They come out exactly, right? Right. What do we get? 5.1 more of O. Right. Any question? Comment, question? Right, now do a practice. So if you can get the formula from the name, and then you see what we did for that question, you should be very easy to get the problem, right? We probably want to get the formula first, then we see if we get the formula right or not. What is our formula? Diphosphorus, that's kind of straightforward. Di means what? Now what do we have else? Pentan, right? Pentan is 5. So therefore our formula is P2O5. If you know it's P2O5, right? And you can write for every 1 P2O5, how many P we have? 2P, right? How many O do we have? 5O. Now the question is you want to calculate how much what? Good. So I want to see your right eye. So where is your equation?
My shit's still on.
But you think it's 3.45, right? It's 3.45 more of what is it? What's the compound? Where is it? Diphosphorus pentyl oxide. So you get that right? So you want to cancel out that one out. You want to find out how many more of oxygen. Right? Well, right now, like what I write there on top of equation, what I write here, this one, right? So you write for every one of that is a P2O5. So you can write 1 of the P2O5, and then you can see 1 more, right? Equivalent to what? How many?
right up. Yeah, so that's what I want to say. I want to see your the work, right? So what
Is
word?
it E?
Huh?
Is it E?
The E.
Because you have to multiply by 5.
Right, multiply by 5. Get that?
Yeah.
Yeah. Okay, now show how your calculation. E. Yeah. You write, did you write? Very good. Do you write out the steps?
What are you playing?
Okay.
Like your ears are working and
Very good.
Oh, why are you playing?
Okay. Very good. I thought like some of you already get familiar with our procedures, so don't forget, check the eye cameras quite often and do the quiz. Read the chapter, read the lecture notes, and do those CIEs. And usually don't do like just one time. You do like one time, not enough. Did you write out the calculations? Yeah, that's what you do. Then where's your? Okay, tell us what you did.
Oh, so they gave you the 3.45 moles of diphosphorus pentoxide, and then, so you know there's, because it's pentoxide, there's 5 moles of oxygen to 1 mole of the whole compound. So then, you just multiply, and your units cancel out, so you get your moles of oxygen.
Then? Right. Any questions? Right, so let's try this one. I think after this one, we will go to the lab, and I will finish this chapter 3 next week. E? Maybe. Right, so this question is a little bit tedious. Okay? There are different ways to solve the problem, but one common way is what I talked about before. You probably first want to use that 2 common steps. Remember those GMN problems? Okay? From gram to mole, from mole to numbers. So you first finish that. What we look at 2 important common steps. You will get how much of this isopropyl molecule as a whole. Then use what you learn in the last section. For every one C3H8O, there are how many C? Okay? Is that right? That makes sense? So we first use the common 2 steps. Okay? Figure out how many C3H8O in that amount of gram of this compound. 2 steps. Right. So what do? You want to get mole from a gram. Already find the answers? This is the 2 common steps, right? So this from gram to mole, use mole mass. From mole to the numbers. What do you see? What do you have here? This is what? This is as a whole, right? This is a whole. Well, this as a whole, so therefore this is C3H8, this mole is also C3H8. And then this is also C3H8 and O. Then on top, you will see that is also this, not atom. This molecule. Very good. You get these 2 steps very solid. Right? The thing about once you have that much of C3H, this question is asking you how much what? You know, how much atom? Then when you use the last step, you want to get the atom from this molecular, what do you use? Right?
Is it like
Whatever you want.
like 3?
Divide by 3. That's you divide out like for this. You want to divide the formula and the converting. This one, the whole can write it somewhere like one more days or 1 day.
But what, like, how do you not
Right now we have this. So we just write, just read this question and this last second when we started. For every 1 day, you don't have to give their number. Just start starting this one. Just say like for every 1 day.
Yeah, that's what I do.
For every 1 day,
No, but mine was like
yeah, for everyone. You can refer to one more or one molecular. Right now, what you get is one, it's not more. Right now, this one 90, that means we won't have more than this. Right? Just write one of these. So I mean, for every one of these, and you have how many combinations? Yeah, they write it in. They're going to use those. Yes, what write it here. Right. Let me see. That's pretty good. Pretty good. Right, is that okay? Okay. Do you get it okay? So this is one more, that mark like have this, you need to monitor before or after. Where's your combination? Yeah. Okay. So what do you? How about tomorrow? Oh, that. Okay, good. Are you okay? Yeah, you first like repeat the 2 steps, or you can just in the middle. You can edit like that, 1, 2, 3 reviews, correct. Yeah. All right, any questions? What do you do? Where are you putting the steps? Right? There's more mass, right? Is that one mass? You can divide by some mass. And that'll be more harder. Then you'll get a pattern. So every one for a color pattern. Alright, I think that you can work on this program. So when we come back next week, we'll finish Chapter-3 and we'll start on Chapter-4. Okay, so that's for the lab now. I'm returning the second lab report, which is CSI.
So what was that? That's what you drink. Yeah, when you drink, you can't fuck. And that is just awkward. I got drunk as shit. What are you taking? Just testosterone. Let's see. There's tests.
Yeah, I know that, but like, how many milligrams?
Oh, 500. I'm taking 250.
Dude, you know what the problem is? What are you drinking?
A lot of whiskey.
Alright, stop with the fire, just stick to vodka. You won't have a problem.
Yeah. Whiskey will do it to you. I'm sitting there like, man,
Whiskey will
I might have to like whip out that shit atlas or something.
Because what do you call it, dude, seriously, like.
I just recorded that.
I've never done that shit, but I can try to take some other tests.
John. You know, I just recorded that.
Yeah.
You're like right in the view.
Hey, it's all good.
Get it lift.
That's you just chill on the check sheet, like, you know,
This is good. I'm telling you, this stuff is one topic for now.
Yeah, dude.
One thing I want to tell you is seriously, like, don't, be careful what you mix. Make sure you don't take a lot of stuff back, because you're gonna start bleeding man days. If you take like aspirin, if you take a lot, like, you know, some people take aspirin. You know, some people take aspirin on a daily basis.
Yeah.
That's all you get, all that stuff. Some people will do that. Like, do that stuff. You really screw up. Like, you'll start bleeding like
That was, I got punched in the face a lot on Saturday, so then I bled all night. Because it was gonna happen again, there's just bloody nose. I'm like, God, this is so unfortunate right now.
Oh, by the way, my stuff might be a little bit,